Okay, we've learned a lot of powerful techniques in lessons 1 through 6, especially in lesson 6, where we put together ideas about and or formulas, using them together, using them with tree diagrams and conditional probability. There's really just a few more topics we need to cover to talk about what I call the backbone kind of main ideas of probability. We need to explore how we use Venn diagrams to solve probability problems. They're just as powerful as using tree diagrams. And then there's one other way that events can be related to each other, and that's one event can be completely contained inside of another one. That's called a subset, and we should look at how that changes the probability calculation. So we'll look at those two topics to kind of round out our ideas of the foundational rules of probability computations. Okay, so in the previous lesson, in lesson 6, we saw how a tree diagram can be used to find probabilities along with formulas. Conditional probabilities in both directions. Venn diagrams are also very useful. Rather than come up with word problems here, we're going to talk about just abstract events that are just labeled with letters, so we can focus just on the structure of the probabilities and the Venn diagram. So let's say we have two events, event C and event D. Probability of event C happening is 30%. Probability of event D happening is 10%. But we're also told the events C and D are disjoint, and we want to compute what the probability is of C and D occurring, C or D occurring, and C given D occurring. Okay, so since they told us that the events are disjoint, it means we could draw a Venn diagram, and we would draw it so the circles don't overlap, because that's what disjoint or mutually exclusive means. It means there's no overlap. And we can go ahead and fill in the probabilities for C and for D. Right? So we should attempt to account for all the probabilities in the diagram. And there's one area that's unaccounted for, the area that's not in C or D. But if we add up 30 and 10, that's 40%. That leaves 60% left over, so that would have to be in the outside. And by the way, with Venn diagrams, you can either fill them in with counts or you can use probabilities, because they're kind of the same thing. If you thought of the universe as having, say, 100 elements in it, then if you fill probabilities in, it would be easy to convert it to counts. It would just be that times 100. So it's equivalent. You just have to stick with one method. Either everything in the diagram is counts, or everything in the diagram is probabilities. And that's true throughout probability. Okay, so let's use our Venn diagram now to compute some probabilities. So the probability of C and D is the intersection, and that there is no intersection here, so that probability simply must be 0. From inspection from the diagram, there's no overlap. That means the probability, the and probability, is 0. Okay, probability of C union D means the union of events C and D, which is just the total probability in the two areas. So if I look at the areas I've shaded in C and shaded in D, it would just be the sum of all of the probability that's spread out in that shaded region. That's 30 plus 10 more is a total of 40%. So just from the adding up the probability in those areas of the Venn diagram, 40%. Probability of C given D means we can first shade the conditional sample space, which would just be the D circle. Recall that the stuff that's after the line gives us the conditional sample space. So out of D, which would be the D circle, the C tells me what probability, how much of that is in C. Well, actually, there's none of that in C, right? The area that's in D that's also in C is nothing, because there's no overlap. So that conditional probability would be 0. Okay, so Venn diagram, if we have disjoint events, it's easy to draw one. We just draw the events so they don't overlap. What if, in this example, we're given two different events, probability of E, which is 50%, probability of an event F, which is 20%, and the events E and F are independent. And we want to find the probability of E and F, E or F, E given F, and F given E. So independence doesn't actually indicate anything about overlap. So in general, we have to assume that the events might overlap. That means we can't initially enter any probabilities, because if we look at this 50% probability for E, how do we know where that is? It's got to be somewhere in the E circle, but some of it is here and some of it is here, and we really don't know how that's divided up. So we're going to have to start with something else. Well, what does independence tell us? Independence, remember, is a special case of the AND formula, and so it would make sense for us to start with the AND formula. If E and F are independent, then the probability of E doesn't depend on F, and that's always the same. That means that the probability of E given F could be written probability of E. That's the simplification that occurs if we have independent events. Likewise, the probability of F doesn't depend on E, so the probability of F is the same as the probability of F given E. So if we start with the general AND formula, let's pick the one where we have E first. The probability of E and F is the probability of E times the probability of F given E. But because we have independent events here, that means that this probability simplifies to just probability of F. And that means we have a simplified version of the AND formula we can use to calculate the overlap. Probability of E and F would be the probability of E, which is 0.5, times the probability of F, which is 0.2, which turns out to be 0.1. And that means we can fill this in the Venn diagram using our probabilities. And we already mentioned this with Venn diagrams. You can fill in either counts or probabilities as long as the whole diagram uses the same thing. Okay, now that we know the overlap, we can fill in the areas inside of only E and only F, because if the probability of E is 0.5, that means the entire probability in the E circle has to add up to 0.5, but we've already accounted for 10%. That means the other 40% has to be over here, and we can fill that in now. And we can use the same idea with the probability of F. If the probability of F is 20% and we've already accounted for 10% of it here, then the other 10% has to be here, and we can fill it into its spot. And then we can say, okay, if we have 40, 50, 60% of the probabilities accounted for, there's only one space left for the rest of the probability, which is 40%, so it must go out here, somewhere outside of the E and the F circles. Now we can find the probability of E or F because it's simply the probability anywhere in E or F together. And so that would be 0.4 plus 0.1 plus 0.1, which is a total of 0.6. And we could find either of the conditional probabilities by remembering that the condition defines the conditional sample space. So if I'm working on the probability of E given F, then I can shade in the F circle, and the bottom of the fraction here is going to be all of the probability in that circle, which is a total of 20%, 0.1 plus 0.1. And then on the top, we're going to have the probability of E. So it's going to be the portion in that circle, which is in E, which is the 0.1. So it's going to be 0.1 out of the 0.2. So 0.1 divided by 0.2 is 0.5. And that means that if F has occurred, then there's a 50% chance that E has also occurred. We can do the same process for the other conditional probability. This time E is establishing the condition, so the E circle, which has a total of 50% of probability in it, that's the probability for the conditional sample space. And then on the top, we're going to take the probability of being in F, which is 10%. So 10% out of the 50%, 20% is the probability of F given E. In other words, if E has occurred, there's a 20% chance that F has also occurred. Alright, so if we have things that are independent, then it allows us generally to find something about the overlap to start. And that's a good thing in general because of this idea that if we have the overlap part, then we can go back and fill in the less specific what's left in E and what's left in F. So this is a general rule. When we fill out Venn diagrams, we always want to start with the most overlap part first. Okay, let's put those ideas to use in a larger problem. Let's say that a campus radio station surveyed 190 students to determine the types of music they liked. And the survey revealed that 114 students liked rock, 50 liked country, 41 liked classical. Also, 14 liked both rock and country, 15 liked both rock and classical, 11 liked classical and country, and 5 liked all three types of music. So if we pick a student at random, what's the probability that they like only rock, that they like exactly one of the three types of music, that they like at least two of the three types of music, or that they don't like rock or country? So when we have a lot of information like this, where we have counts and even especially things that appear to be overlapped, like rock and classical or all three types of music, that's a clue that we should be using a Venn diagram to combine this and contain this and organize this information. Okay, so in this case, we'll use the first paragraph here to generate the Venn diagram itself. So we'll need a circle for each type of music, and since 5 people liked all three, it looks like all the circles must mutually overlap in some way. So we'll use our idea that we should fill in Venn diagrams from the inside out, and this one, because we're given counts of students instead of probabilities, we're going to fill in this Venn diagram with counts instead of probabilities like we did in the other examples here. The middle section would be for the 5 students who liked all three types of music, so we'll fill a 5 in there in the middle. And then if we use this phrase here that 14 liked both rock and country, well, both rock and country is the overlap of the rock and country circles, which is this blue area here, right? But we've already accounted for 5 of that, and that means that 14 minus 5, or 9, are left that could go in the rest of that shaded area. That's why this area here contains 9, because 9 plus 14 together adds up to the 14 that like both rock and country. Okay? So using the same idea, we know that there are 15 people who like both rock and classical, and there's 11 who like both classical and country, and from each we would subtract the 5 in the middle that we already know. So when I work on the rock and classical, that would be this area. If there's 15 but 5 are already accounted for, that leaves 10. That would go here. And then if there are 11 who like both classical and country, that's this area. And we've already accounted for 5, that leaves 6 to go in this location. So we can, from the inside out, work our way out. Now we can use the fact that 114 total liked rock. That means there needs to be 114 total students in the rock circle. But we've already accounted for 9, 5, and 10, which is a total of 24 of those. So if I take 24 and subtract it from 114, there's 90 students left, and the only place they can be is in this portion, in the rock circle, in the place where we haven't already accounted for that. And we can use a similar reasoning with the 50 people who liked country to subtract off these parts in here to fill this in. And we can also use the 41 that like classical and add up the 6 and the 5 and the 10 here and subtract that to get 20 are left there. And then finally there's one other spot outside of all the circles, because we surveyed a total of 190 students. So if you add all of the numbers in all of the circles up and subtract that from 190, there are 20 other students left unaccounted for. They have to be outside all the circles. They must like none of these 3 types of music. Okay, so at this point we have the Venn diagram is complete. Now we'll switch to the questions part of the problem, and we'll find the probabilities that they're asking for. So for part A, it asks for the probability that somebody only likes rock. This is a simple, not a conditional probability, and that means that we're going to make a fraction where the bottom is all 190 students, right? And in this case, every student has an equally likely chance of being selected, so we'll use the equally likely cases situation where we just take a number out of a total. The total number is 190, and then the number on top has to be the number of students who only like rock. So the students who only like rock is this 90 right up here, right? That's the other parts that are in the rock circle also like classical, or also like country, or also like all 3. So the 90 is the people who only like rock. So 90 out of 190 would be 47.37%. Okay, for part B, the probability that a student selected at random likes exactly one of the 3 types of music. Since there's no line here, this is not a conditional probability. The denominator of the fraction is still 190, but the numerator would now be all of the ways to like exactly one type of music. So these people like exactly only rock, these 30 like only country, and these 20 like only classical. So if I added those up, that's the number of people who like exactly one type of music. Out of the 190, 73% of the people like only one type of music. For part C, it says, what's the probability of at least 2 of the 3 types of music? The denominator is still 190, right? But now we're talking about people that like at least 2. So the 9 and the 10 and the 6 are people who like exactly 2, and the 5 are people who like 3, which is also at least 2. So we would have to add up these 4 blue numbers for the numerator divided by the 190. So there are about 16% of students who like at least 2 types of music. And then for this one, the last one, D, the probability that someone does not like rock or country, the denominator is still 190, but now the numerator will be all the students that are just not in the rock circle or the country circle. So let me just X out the rock circle. They can't be in the rock circle. They can't be in the country circle, right? Any number that's not in there. So it would be this 20 and this 20. So 40 out of 190, which is 21%. Okay, so Venn diagram is a great way to organize a large amount of information, especially when there's apparent overlaps. Very flexible technique. Okay, one last thing to wrap up the basic ideas of probability rules and basic computation ideas. We've seen lots and lots of examples of and or cases, and of disjoint and overlapping events here. There's one other way that 2 events can be related, and that's if one event is entirely contained inside the other event. That is called a subset. right? I know each of these events is a subset of the universe, right? But sometimes an event like A could be completely a subset of B. That means everything in A is in B, but there's other things in B besides the A. So let's use this abstract example. Let's say that there's an event A whose probability is 30%, and there's an event B whose probability is 60%, but we're told that A is a subset of B. Could we find things like the probability of A and B, the probability of A or B, and the conditional probabilities? Okay, so first we can start with the most overlapped region, which in this case would be the circle A, right? We know that that probability is just A, so that is just 30%, so we'll just fill that in. Okay. We also know that the probability of B is 60%. That means everything in the B circle has to be 60%, but we've already accounted for 30%, which means the other half of that, the 30%, has to be in the rest of B. Right, so we could fill that in as well. And then we know that if we've accounted for 60%, there's still 40% unaccounted for. That would have to be in the rest of the universe out here. So 40% out there. So now we have a completely filled in Venn diagram, and now we can use it to compute probabilities. So for the AND case, the probability of A and B would be the overlap. So if we just remember that AND is the intersection or overlap, well, A itself is completely overlapping B. So the part that's overlapped is just the probability of A. So that would be 30%. Probability of A or B. For the union, it's anything that's in A or B or both. And everything in A is also covered by being in B, so the union is just the circle B. So it's going to be the total probability in the B circle, which is 60%. The probability of A given B, remember that the B is the condition, so that establishes the conditional sample space. So we'll use the 60% that's in B. We'll write the probability of B as the denominator of our fraction here. And then the numerator has to be the part of that blue shaded region that's also in A. And so that would be the 30%. So it's 30% over 60%, and therefore 0.5. And what that's saying is, given that B has occurred, there's a 50% chance that A is also occurring. If we reverse it, the probability of B given A, then the A circle forms the conditional sample space, so that would be 30%. So we'll shade that. And then the numerator is going to be the part of B, the part of the shaded region of A that's also in B. So everything in that blue is also in B, so that's going to be 30% out of 30% or 100%. So another way of saying that is, given that A has occurred, there is a 100% chance that B has also occurred, because A is completely inside of B. So just to extend this, we might also ask if these events are disjoint or independent. So the events would be disjoint if there's no overlap. But from the diagram, it's really clear that they do overlap, so we would be able to state the events are not disjoint. They're not mutually exclusive. And as far as independence, to test independence, we should check whether one of the event probabilities is changing depending upon the other event. So let's choose A to check. We can find two probabilities of A. We'll find the probability of A, and we'll find the probability of A given B. Right, well, the probability of A was given in the problem. That was 30%. And the probability of A given B, we computed earlier. The probability of A given B was 50%. So since those two probabilities are not the same, it means the probability of A seems to depend on the probability of B. So we would have to say that A and B are not independent events. All right, so that's a good coverage of the rest of the topics. There's a lot of things we can do with the probability ideas and computation techniques and diagrams in lessons 1 through 7. So if you want to check out the examples video, we'll do some additional examples using the stuff in this video. And then if you jump to the very end, the last lesson is talking about putting all of the ideas together from the entire lesson series and how to distinguish which strategy to use, which is often the most difficult thing.